Okay, so heat is a great source of energy, right? And it's really potentially powerful to take heat and turn it into mechanical energy. And that's all about what heat engines do. Now, it's easy to get heat from mechanical energy. It's easy to get heat, right? If we rub our hands together, we generate heat. It's more difficult to use that heat generated to do something, right? To do work, to get mechanical energy out of it. And so we're going to look at that process and the efficiencies of that process and how we use the second law of thermodynamics to analyze how engines work. All right. So when we think about using heat for work, we want to define a few variables. The first is that we have sort of the input heat. Okay, we're going to call that QH, right? The input heat, how much heat we have in the system or that we're going to put into using for work. We then, of course, have the work. This is the work we get out of the input heat. And then we have kind of what's wasted or the leftover heat that wasn't all the way used for work. Because again, it's hard to do that. It's hard to do it. So this is the output heat. Now, according to conservation, right, our input heat should equal the work plus our output heat. That's pretty straightforward. Now, in this case, we are going to look at all of these as positive variables, okay? So in the terms of a heat engine and a refrigerator, these are all positive, okay? When we talked about heat in terms of the first law of thermodynamics, remember we had those positive and negatives we had to pay attention to. In this case, when we're talking about the engine or the refrigerator, all of these values are positive, all right? Okay, so where does this heat come from? Where does that heat come from? Well, that's the heat that we've obtained perhaps by burning fuel, like in a steam engine or a combustible engine. Or perhaps this is the heat from a compressed gas or a compressed fluid, right? As we might see in like a refrigerant. So where that heat comes from, we have to input that heat, and then we have to use that heat in our engine, all right? Again, how much we get also is conserved from, so we can kind of go back the line a little bit in terms of the heat. Okay, so how about efficiencies? So this is a pretty straightforward relationship, and there's kind of this idea of if this is describing an engine, how effective is this engine? How much work do I get out? And how much waste do I have? How much heat do I have leaving the environment, or leaving to the environment, excuse me. And so we use this idea of lowercase e, which represents our efficiency, right? And the efficiency, as you might expect, is just the ratio of how much work I got out to how much heat I put in. So how much work did I get out to how much heat I put in? Now, if we rewrite this equation and substitute our relationship up here, this also equals 1 minus the ratio of the waste to the input. You can do that algebra. Okay, so this is our efficiency relationship. All right, how efficient is our engine? Now, we often talk about efficiencies in percentages. So if I want to convert this to a percent, I would multiply by 100 to get the percent efficiency. Okay, so just kind of keep that in mind, like any percentage, right? So is that accurate? If I have a 100% efficient engine, that means all of the heat goes into my mechanical work. So there is no loss, heat loss, and this ratio is 0, so I get 1, comes under 100%. So that kind of gives you that framework. Okay, let's just do a quick example using this relationship and thinking about it in kind of a real scenario. All right, let's imagine that we have an auto engine and it has an efficiency of 18 efficiency of 18%. This engine can produce 200 joules of work per second. How much heat input is required and how much heat is wasted? So just giving this relationship some practice. So first of all, we want to know how much heat is required. Well, that is related to our efficiency. So we're told that the efficiency is 0.18. We know that the work output of this engine is given as 202.2 kilojoules. So 22,000 joules is the work divided by how much is inputted is what we want to know. So that's our QH. So QH is equal to 22,000 divided by 0.18. And we find that our heat needed is 1.22 times 10 to the 5th joules. So a lot of heat needed. All right. And to, again, just sort of practice this relationship, how much heat is wasted in the environment? Well, again, we can use the relationship for our efficiency. So our efficiency is equal to 1 minus QL over QH. And so I can now solve for QL, and that is going to be equal to 1 minus E times QH. Okay, so you can do that algebra there. It's equal to, do I have space over there? I do. I think, oh, nope, I ran out of room. This is equal to QL. Perfect. All right, so QL is equal to 1 minus 0.18 times my QH, 1.22 times 10 to the 5th, and my loss to the environment is 1 times 10 to the 5th joules. All right, so every second that this engine puts out 22,000 kilojoules of work, or joules of work, so 22 kilojoules of work, every second we lose 1 times 10 to the 5th joules, so 10 kilojoules, 100 kilojoules of energy to the environment, and we needed 122 kilojoules of energy to operate. All right, so that's an example of using heat engines and their efficiency. Now, this takes heat in and produces work. What if I wanted to produce cooler temperatures, like in a refrigerator? What if I wanted my output heat to be something that I am looking for? A reverse process, so to speak, right? Refrigerators are kind of like a reverse process. In this situation, I take heat from my environment and I want to take that heat and put it out into the world. Okay, so I'm focused on the lower temperature heat. All right, so what does that look like? How much heat goes into it? How much work do I have to do in order to get that lower temperature out? So if we think about refrigerators and air conditioners, we think about their performance, right? And a refrigerator and air conditioner's efficiency is described as its performance, and it's called the coefficient of performance, or COP. So we're going to talk about that a little bit and then use an example. So like a heat engine, we take heat to do work. In this situation, we're taking work to reverse the process of taking cold air and moving it towards warmer air, or taking warmer air and taking heat out of the cold air, cold space, and moving it outward. All right, so in this case, our coefficient of performance is equal to the lower temperature heat over how much work it took to do that. All right, how much work it took to do that. And so if I look again at my relationship for work, this then is provided as that lower temperature over the difference between the heat and in the higher area to the heat in the lower area. So that's just a relationship of that work equation. Okay, so how do we use the coefficient of performance to analyze a situation? Well, let's look at an example. So this sort of material, which is all founded on the conservation of energy, which is all founded on, which is then applied to the second law of thermodynamics, is relatively straightforward information that we can then use fun examples to explore and understand a little bit better. So freezer has a coefficient of performance of 3.1. It uses 200 watts of power, right? 200 watts of power. Now remember, power is the amount of work per time. So we want to keep in mind that power is equal to the work per time. Okay, so we're going to keep that in mind. How long does it take to freeze an ice cube tray that contains 500 grams of water at 0 degrees? So if I have 0 degrees of water and I put it in to that freezer, how long is it going to take for that freezer to freeze that water when it's already at 0 degrees? And think about, what if it wasn't at 0 degrees? Well, it would take more energy, right? You'd have to cool it first. So we're just going to do a shorter example, but that's part of the process. How much energy would it take? Okay. So the first question is, how much energy is needed to go from 0 degrees to freeze? That's a phase change. And when we think about the amount of heat needed to be removed from that ice cube tray, we need to think about the latent heat, right? So the amount of heat needed to remove that heat, the amount of heat to remove from the ice cube tray to freeze it, is equal to the mass of the ice times the latent heat of fusion. We're going through the two. So L in this case is the latent heat of fusion. All right, so we have 0.5 kilograms of ice, 500 grams, times the latent heat of fusion for water is 3.33 times 10 to the 5th kilogram, or joules per kilogram. And so it's the case that we are going to need 1.66 times 10 to the 5th joules of heat removed from that ice. So the amount removed, our heat output, the amount removed has to be 1.66 times 10 to the 5th. We know that our coefficient of performance, remember, is the amount of heat, how much work it takes, how much work it took to get that amount of heat, the ratio of the amount of heat that was removed to the amount of work that it took to remove that heat, okay? And we know that that tells us that the work is equal to the heat over the coefficient. So I just rearranged this equation. So how much work will it take to get rid of that heat? It will take, since I need this much heat, and I run at an efficiency of 3.1, it's going to, how much work do I need to do? We need to do, or the freezer, 5.37 times 10 to the 4th joules of work is going to be needed to cool that ice enough that it fully freezes. All right, so we first have to determine how much heat needs to be removed based on the efficiency, which we call the coefficient of performance. For a refrigerator, for that process, air conditioner would be the same thing. We need to look at, not the same number, but the same idea. We need to look at the coefficient of performance relative to how much heat I need. That tells me how much work needs to be done. I know how much work the freezer can do, and so it per time, right? How much work it can do every second. So if this is how much work I need, then the time is going to be the work needed over the power rating of that freezer. And so I need 5.37 times 10 to the 4th divided by my power, which was 200 watts. That gives me 268 seconds, which equals 4 minutes. So it'll take 4 minutes for that tray of ice cube to freeze solid once it's at 0 degrees. So that's kind of fun. Next time you run out of ice at a party, you can figure out exactly how long it's going to take to get another tray of ice. You can wow all your friends. All right, so using these ideas of efficiency, heat engines, refrigerators, the second law of thermodynamics, conservation of energy, all wrapped up in one. Good job.